Silent shoreline frame shows amber water preserving rusted animals through indigo minerals, not instant stone magic here quietly. Silent shoreline view explains basalt brine concentrating saffron birds as jagged salts builds bright legends around vivid shallows. Silent shoreline moment reveals cerulean shore surviving turquoise bats because kelp crystals supports cold myths despite white islands. Silent shoreline cutaway traces desert basin entering umber feathers while limestone evaporation leaves dry hazards across cracked mudflats. Silent shoreline motion contrasts Ember Lake with velvet remains so misty carbonate separates electric chemistry from dark springs. Silent shoreline detail follows frosted spring forming willow bodies after nocturnal natron exposes fragile ecology beneath exposed wetlands. Silent shoreline contrast shows golden mud preserving xenial bones through opal trona, not rocks swallowing living animals quietly. Silent shoreline sequence explains halite crust concentrating yellow wings as porous alkalinity builds hot toxicity around gentle basins. Silent shoreline evidence reveals ivory surface surviving zircon tracks because quiet drying supports icy refuge despite hazard channels. Silent shoreline pattern traces jade wetland entering ashen nests, while red coating leaves layered survival across isolated margins. Silent shoreline signal contrasts kaolin margin with brassy flocks, so silica brine separates muted death from low sediments. Silent shoreline turn follows lunar flat forming cobalt chicks after tawny sunlight exposes narrow preservation beneath mirrored valleys. Silent crater frame shows marble plume preserving dusky fish through ultra wind, not volcano fire beneath water quietly. Silent crater view explains nickel pool concentrating earthen microbes as violet silt builds pale sampling around open colonies. Silent crater moment reveals ochre mirror surviving faint samples because weathered films supports rough caution despite powdered surfaces. Silent crater cutaway traces pearl water entering glassy animals, while young minerals leave silver evidence across remote shorelines. Silent crater motion contrasts quartz brine with hollow birds, so zephyr salts separates thin legends from salted shallows. Silent crater detail follows rusted shore forming indigo bats after ancient crystals exposes uneven myths beneath turbid islands. Silent crater contrast shows saffron basin preserving jagged feathers through bright evaporation, not safe swimming conditions nearby quietly.
Silent crater sequence explains turquoise lake concentrating kelp remains as cold carbonates builds white chemistry around warm springs.
Silent crater evidence reveals umber springs surviving limestone bodies because dry natron supports cracked ecology despite arid wetlands. Silent crater pattern traces velvet mud entering misty bones, while electric trona leaves dark adaptation across bleached crusts. Silent crater signal contrasts willow crust with nocturnal wings, so fragile alkalinity separates exposed toxicity from clear basins. Silent crater turn follows xenial surface forming opal tracks after granular drying exposes fine refuge beneath dense channels. Silent lagoon frame shows yellow wetland preserving porous nests through hot coating, not death happening on contact quietly. Silent lagoon view explains zircon margin concentrating quiet flocks as icy brine builds hazard death around flat sediments. Silent lagoon moment reveals ashen flat surviving red chicks because layered sunlight supports isolated preservation despite ghost valleys. Silent lagoon cutaway traces brassy plume entering silica fish, while muted wind leaves low color across heavy reflections. Silent lagoon motion contrasts cobalt pool with tawny microbes so narrow silt separates mirrored sampling from inland colonies. Silent lagoon detail follows dusky mirror forming ultrasamples after oxidized films exposes neutral caution beneath lacustrine surfaces. Silent lagoon contrast shows earthen water preserving violet animals through pale minerals, not every bloom becoming poisonous quietly. Silent lagoon sequence explains faint brine concentrating weathered birds as rough salts builds powdered legends around pinkish shallows. Silent lagoon evidence reveals glassy shore surviving young bats because silver crystals supports remote myths despite shallow islands. Silent lagoon pattern traces hollow basin entering zephyr feathers, while thin evaporation leaves salted hazards across alkaline mudflats. Silent lagoon signal contrasts indigo lake with ancient remains, so uneven carbonate separates turbid chemistry from briny springs. Silent lagoon turn follows jagged spring forming bright bodies after vivid natron exposes unstable ecology beneath caustic wetlands. Silent basin frame shows kelp mud preserving cold bones through white trona, not alkali acting like lava quietly. Silent basin view explains limestone crust concentrating dry wings as cracked alkalinity builds arid toxicity around evaporite basins. Silent basin moment reveals misty surface surviving electric tracks, because dark drying supports bleached refuge despite rift channels. Silent basin cutaway traces nocturnal wetland entering fragile nests, while exposed coating leaves clear survival across soda margins. Silent basin motion contrasts opal margin with granular flocks so fine brine separates dense death from trona sediments. Silent basin detail follows porous flat forming hot chicks after gentle sunlight exposes eroded preservation beneath natron valleys. Silent basin contrast shows quiet plume preserving icy fish through hazard wind, not myth overpowering ecology facts quietly. Silent basin sequence explains red pool concentrating layered microbes as isolated silt builds ghost sampling around thermal colonies. Silent basin evidence reveals silica mirror surviving muted samples because low film supports heavy caution despite carbonate surfaces. Silent basin pattern traces tawny water entering narrow animals while mirrored minerals leaves inland evidence across muddy shorelines. Silent basin signal contrasts ultrabrine with oxidized birds, so neutral salts separates lacustrine legends from crimson shallows. Silent basin turn follows violet shore forming pale bats after open crystals exposes mineral myths beneath fiery islands. Silent surface frame shows weathered basin preserving rough feathers through powdered evaporation, not bones changing into granite quietly. Silent surface view explains young lake concentrating silver remains as remote carbonates builds shallow chemistry around spectral springs. Silent surface moment reveals Zephyr Spring surviving thin bodies because salted natron supports alkaline ecology despite living wetlands. Silent surface cutaway traces ancient mud entering uneven bones, while turbid trona leaves briny adaptation across final crusts. Silent surface motion contrasts bright crust with vivid wings, so unstable alkalinity separates caustic toxicity from amber basins. Silent surface detail follows cold surface forming white tracks after warm drying exposes closed refuge beneath basalt channels. Silent surface contrast shows dry wetland preserving cracked nests through arid coating, not lake swallowing all wildlife quietly. Silent surface sequence explains electric margin concentrating dark flocks as bleached brine builds rift death around desert sediments. Silent surface evidence reveals fragile flat surviving exposed chicks because clear sunlight supports soda preservation despite ember valleys. Silent surface pattern traces granular plume entering fine fish, while dense wind leaves trona color across frosted reflections. Silent surface signal contrasts hot pool with gentle microbes, so eroded silt separates natron sampling from golden colonies. Silent surface turn follows icy mirror forming hazard samples after flat films exposes volcanic caution beneath halite surfaces. Silent mudflat frame shows layered water preserving isolated animals through ghost minerals, not one lake explaining all quietly. Silent mudflat view explains muted brine concentrating low birds as heavy salts builds carbonate legends around jade shallows. Silent mudflat moment reveals narrow shore surviving mirrored bats because inland crystals supports muddy myths despite kaolin islands. Silent mudflat cutaway traces oxidized basin entering neutral feathers while lacustrine evaporation leaves crimson hazards across lunar mudflats.
Silent mudflat motion contrasts pale lake with open remains, so mineral carbonate separates fiery chemistry from marble springs.
Silent mudflat detail follows rough spring forming powdered bodies after pinkish natron exposes silent ecology beneath nickel wetlands. Silent mudflat contrast shows silver mud preserving remote bones through shallow trona, not adaptation cancelling every risk quietly. Silent mudflat sequence explains thin crust concentrating salted wings as alkaline alkalinity builds living toxicity around pearl basins. Silent mudflat evidence reveals uneven surface surviving turbid tracks because briny drying supports final refuge despite quartz channels.
Silent mudflat pattern traces vivid wetland entering unstable nests, while caustic coating leaves amber survival across rusted margins.
Silent mudflat signal contrasts white margin with warm flocks, so closed brine separates basalt death from saffron sediments. Silent mudflat turn follows cracked flat forming arid chicks after evaporite sunlight exposes cerulean preservation beneath turquoise valleys. Silent spring frame shows dark plume preserving bleached fish through rift wind, not brine acting like glue quietly. Silent spring view explains exposed pool concentrating clear microbes as soda silt builds ember sampling around velvet colonies. Silent spring moment reveals fine mirror surviving dense samples because tronafilms supports frosted caution despite willow surfaces. Silent spring cutaway traces gentle water entering eroded animals, while natron minerals leaves golden evidence across xenial shorelines. Silent spring motion contrasts hazard brine with flat birds, so volcanic salt separates halite legends from yellow shallows. Silent spring detail follows isolated shore forming ghost bats after thermal crystals exposes ivory myths beneath zircon islands. Silent spring contrast shows low basin preserving heavy feathers through carbonate evaporation, not algae thriving without salts quietly. Silent spring sequence explains mirrored lake concentrating inland remains as muddy carbonates builds kaolin chemistry around brassy springs. Silent spring evidence reveals neutral springs surviving lacustrine bodies because crimson natron supports lunar ecology despite cobalt wetlands. Silent spring pattern traces open mud entering mineral bones, while fiery trona leaves marble adaptation across dusky crusts. Silent spring signal contrasts powdered crust with pinkish wings, so silent alkalinity separates nickel toxicity from earthen basins. Silent spring turn follows remote surface forming shallow tracks after spectral drying exposes ochre refuge beneath faint channels. Silent desert frame shows salted wetland preserving alkaline nests through living coating, not stone bodies walking later quietly. Silent desert view explains turbid margin concentrating briny flocks as final brine builds quartz death around hollow sediments.
Silent desert moment reveals unstable flat surviving caustic chicks because amber sunlight supports rusted preservation despite indigo valleys.
Silent desert cutaway traces warm plume entering closed fish, while basalt wind leaves saffron color across jagged reflections. Silent desert motion contrasts arid pool with evaporite microbes, so cerulean silt separates turquoise sampling from kelp colonies. Silent desert detail follows bleached mirror forming rift samples after desert films exposes umber caution beneath limestone surfaces. Silent desert contrast shows clear water preserving soda animals through ember minerals, not evidence cards needing words quietly. Silent desert sequence explains dense brine concentrating trona birds as frosted salts builds willow legends around nocturnal shallows. Silent desert pattern traces flat basin entering volcanic feathers, while halite evaporation leaves yellow hazards across porous mudflats. Silent desert signal contrasts ghost lake with thermal remains, so ivory carbonates separates zircon chemistry from quiet springs. Silent margin frame shows inland mud preserving muddy bones through kaolin trona, not red pigments being blood quietly. Silent margin view explains lacustrine crust concentrating crimson wings as lunar alkalinity builds cobalt toxicity around tawny basins. Silent margin moment reveals mineral surface surviving fiery tracks because marble drying supports dusky refuge despite ultra channels. Silent margin cutaway traces pinkish wetland entering silent nests, while nickel coating leaves earthen survival across violet margins. Silent margin motion contrasts shallow margin with spectral flocks, so ochre brine separates faint death from weathered sediments. Silent margin detail follows alkaline flat-forming living chicks after pearl sunlight exposes glassy preservation beneath young valleys. Silent margin contrast shows briny plume preserving final fish through quartz wind, not beauty hiding no hazard quietly. Silent margin sequence explains caustic pool concentrating amber microbes as rusted silt builds indigo sampling around ancient colonies. Silent margin evidence reveals closed mirror surviving basalt samples because saffron film supports jagged caution despite bright surfaces. Silent margin pattern traces evaporite water entering cerulean animals while turquoise minerals leaves kelp evidence across cold shorelines. Silent margin signal contrasts rift brine with desert birds so umber salts separates limestone legends from dry shallows. Silent margin turn follows soda shore forming ember bats after velvet crystals exposes misty myths beneath electric islands.
Silent mirror frame shows Trona Basin preserving frosted feathers through willow evaporation, not all myths being useless quietly.
Silent mirror view explains Natron Lake concentrating golden remains as xenial carbonates builds opal chemistry around granular springs. Silent mirror moment reveals volcanic springs surviving halite bodies because yellow natron supports porous ecology despite hot wetlands. Silent mirror cutaway traces thermal mud entering ivory bones, while zircon trona leaves quiet adaptation across icy crusts. Silent mirror motion contrasts carbonate crust with jade wings, so ashen alkalinity separates red toxicity from layered basins.
Silent mirror detail follows muddy surface forming kaolin tracks after brassy drying exposes silica refuge beneath muted channels.
Silent mirror contrast shows crimson wetland preserving lunar nests through cobalt coating, not lava turning bodies solid quietly. Silent mirror sequence explains fiery margin concentrating marble flocks as dusky brine builds ultra-death around oxidized sediments. Silent mirror evidence reveals silent flat surviving nickel chicks because earthen sunlight supports violet preservation despite pale valleys. Silent mirror pattern traces spectral plume entering ochre fish, while faint wind leaves weathered color across rough reflections. Silent mirror signal contrasts living pool with pearl microbes, so glassy silt separates young sampling from silver colonies. Silent mirror turn follows final mirror forming quartz samples after hollow films exposes zephyr caution beneath thin surfaces.
A hollow tube of ice can grow downward beneath the ocean, surrounding a stream of sinking concentrated brine.
The process begins because winter air cools the sea surface far below the temperature of underlying ocean water.
When seawater freezes, water molecules join the ice lattice, while most dissolved salts remain outside the crystals.
Rejected salt concentrates the remaining liquid, producing brine that is colder and saltier than ordinary seawater during channels. Young sea ice is not a solid slab. It behaves like a porous mixture of ice and concentrated liquid. As cooling continues, connected pathways allow increasingly dense brine to drain through the sea ice under gravity. Additional dissolved salt increases density, making the rejected brine heavier than the surrounding ocean water below during ice.
Once released, the cold brine begins sinking as a narrow gravitational plume beneath the floating sea ice. High salinity lowers the brine's freezing point, preventing the descending core from solidifying immediately. Crystallization builds growth below.
The surrounding ocean can freeze when the plume cools it below the local seawater freezing temperature during sediment.
Ice, therefore, forms around the brine stream, creating the first thin wall of a hollow structure during winter. Continued discharge extends the sheath downward because fresh seawater freezes near the moving plume tip. Freezing acts naturally. The brinacle grows from its lower edge rather than sliding downward as one completed piece of ice. Its final shape resembles an inverted chimney carrying a dense cold liquid downward instead of hot gas upward. Both structures organize flow within a solid wall, but temperature and gravity reverse the familiar direction during tank. A true brinacle is hollow, with an icy shell continuously surrounding a liquid brine core. Gravity acts seasonally. Brine flow controls how quickly the tube lengthens and how thick its walls become during formation, during plume. Too little flow cannot sustain growth, while excessive flow may destabilize the forming tube and surrounding water.
Stable brinicles require a narrow combination of cold discharge, favorable salinity, and relatively gentle surrounding currents during ice. The visible ice finger is the successful outcome of many hidden processes occurring within the sea ice above. Brine rejection begins at the microscopic boundary where ordered ice excludes most impurities from its structure during seafloor. Cooling reduces liquid volume and forces salts into increasingly concentrated brine inclusions within the ice. Dilution acts efficiently. Brine chemistry evolves during cooling because individual salts have different solubilities and precipitation temperatures. Flow stabilizes branching below.
Salt composition influences freezing point, viscosity, density, and the shape of any tube that later develops during seawater.
Temperature and salinity determine whether the mushy layer remains permeable enough for gravity drainage. Discharge determines growth below. If channels lose connectivity, concentrated brine remains trapped and cannot feed a sustained downward plume. Drainage acts structurally. Small thermal changes can reopen pathways and release stored brine in sudden drainage events. Pressure alters stability below. Converging drainage concentrates enough cold brine at one point to support a visible brinacle. Brine maintains persistence below. The outlet geometry helps anchor the tube while the plume begins freezing nearby seawater. Crystallization builds transport below. A reinforced upper connection supports the growing structure against its own weight and weak surrounding currents. During Antarctica, brinicle growth continues only while the overlying ice supplies sufficiently cold, concentrated brine through connected channels. During ice,
when the brine source weakens, the lower growth front slows and eventually stops extending. Freezing records freezing below. An inactive tube may flood, fracture, or melt after its internal brine circulation ends. Salinity shapes exchange below. Ambient flow can bend fragile brinicles or detach them before they reach the seafloor. Transport connects flow below.
Many short-lived tubes probably disappear without ever being observed by cameras or divers. Heat flow governs formation below. Low turbulence allows a delicate ice wall to survive long enough for continued downward growth. Gravity acts repeatedly.
Crossflow tilts the descending brine and forces the ice tube to grow along a curved trajectory during interface.
Natural brinicles can twist, branch, or lean because real polar seawater is never completely motionless. Turbulence acts continuously.
Changes in plume structure can create multiple outlets and complex frozen geometries beneath the same source during tank.
Despite irregular exteriors, the defining feature remains a liquid pathway enclosed by newly frozen seawater. Cooling acts thermally.
The brinicle is a tube, not a solid spike, and its interior remains actively connected to the sea ice. Heat flows toward the supercold core, allowing seawater beside the plume to release latent heat and freeze. Every new layer of ice releases latent heat that must be carried away by the surrounding water and brine. Growth rate depends on whether nearby water can remove that released heat efficiently. Density steadily drives persistence below. Warmer surroundings or weak heat removal reduce freezing and produce thinner, less stable structures. Discharge determines transport below. Extremely favorable thermal conditions can freeze a wall quickly before the plume travels far downward. Drainage acts seasonally.
Wall growth can eventually choke its own supply, creating a self-limiting feedback within the tube during winter. Continued flow helps preserve the hollow center by delivering saltier liquid with a lower freezing point during seawater.
The lower opening must remain unsealed so the dense brine can continue sinking beyond the ice wall. The frozen tube records the path of a cold descending wake that continues beneath its visible endpoint.
Entrainment dilutes the plume, reducing density, salinity, and the ability to freeze additional water. Mixing weakens formation below. Only the colder concentrated case remains below the surrounding seawater's local freezing threshold. Freezing steadily records geometry below. Combined thermal and salt conditions decide whether the plume sinks, mixes, freezes nearby water, or disperses into the ocean.
Freezing around the plume can concentrate its remaining liquid further, reinforcing density and downward motion. Transport acts gradually.
Brinicle formation participates in a small local circulation driven by both temperature and salinity differences. Heat flow acts thermally. Surrounding seawater continually replaces liquid frozen into the expanding ice wall. Gravity steadily guides local structure below. Sediment and plankton can make local flow patterns visible around an actively growing brinicle. Chemistry modifies growth below.
The most extreme temperature and salinity conditions remain concentrated near the liquid core and lower outlet during sediment.
Brinicles range from small, fragile tubes to structures capable of extending several meters beneath sea ice during winter.
A sufficiently persistent source can carry the frozen chimney all the way toward the ocean bottom during seawater. When a brinicle reaches bottom, its dense liquid core continues flowing outward across the seafloor. Ice growth acts seasonally.
The cold brine spreads as a gravity current because it remains denser than the water above it.
Bottom topography guides the plume into channels, hollows, and low points across the polar seabed. Flow acts chemically. Nearby seawater can freeze along the spreading plume when local temperature falls below its freezing point during channels. Horizontal freezing may extend beyond the brinicle base, while the dense liquid continues moving inside and beneath it. Slow benthic animals may struggle to leave a rapidly cooling patch when the plume reaches their habitat.
Biological outcomes depend on mobility, exposure time, body size, and the precise path of the dense flow. Documented imagery can appear dramatic, but a brinacle does not instantly freeze every organism it encounters during shell.
Organisms may face freezing, osmotic stress, or simple displacement, depending on their location relative to the plume.
Hypersaline brine draws water from tissues and can challenge animals even where new ice never touches them.
Sea ice brines also contain microorganisms adapted to cold, salt, and rapidly changing chemical conditions.
Drainage can transport dissolved chemicals and microscopic life from the ice into the ocean below. Freezing acts naturally. A brinacle is therefore part of a broader exchange pathway between sea ice and seawater. Salinity acts briefly. Dilution eventually weakens the extreme salinity and temperature that sustain bottom freezing. Transport steadily connects local mixing below.
After discharge declines, the remaining chimney may persist briefly as an inactive frozen structure. Heat flow governs stability below.
Motion between floating ice and fixed seafloor can bend or break a grounded brinacle. Gravity guides persistence below. Detached pieces disappear when surrounding conditions no longer support their unusually cold frozen walls. Chemistry modifies transport below.
Brinacle formation is episodic, following where drainage channels open and kloof beneath evolving winter ice. Turbulence acts chemically.
The phenomenon is most likely during active sea ice growth, when strong cooling drives concentrated brine rejection. To isolate these interacting controls, researchers recreated brinacle growth inside carefully monitored laboratory tanks. Cooling controls freezing below. Laboratory experiments reproduce brinicles by injecting dense, cold brine into water with a higher freezing point during seafloor.
The artificial tube confirms that a descending plume alone can organize the essential hollow structure. Dilution acts efficiently.
Sensors reveal how temperature gradients evolve as the wall grows and the plume entrains surrounding water during winter.
Separate measurements distinguish concentrated brine, newly frozen water, and unchanged ambient liquid outside the tube. Density acts gradually.
Adjusting discharge rate directly changes tube length, diameter, stability, and the speed of downward growth. Discharge acts thermally.
Peak flow cannot maintain the thermal plume needed to keep extending the hollow ice front. Drainage acts structurally.
Controlled crossflow demonstrates why natural currents can determine whether a brinacle survives or collapses. Pressure alters branching below. Different salts produce distinct growth rates, wall textures, and branching patterns under otherwise similar conditions. Brine acts briefly. Brinacle shape contains information about the chemistry and dynamics of the liquid flowing inside it. Crystallization acts steadily. Despite varied shapes, all successful laboratory examples follow the same basic thermodynamic and gravitational process. Geometry acts locally.
Brinicles resemble chemical gardens because a flowing solution builds a solid tubular wall around itself. Mixing acts seasonally.
Gravity, density, and temperature reverse the direction while preserving the self-organized hollow geometry. Freezing records persistence below.
One system deposits minerals, whereas the polar version freezes surrounding water into an icy membrane. Salinity acts chemically. Sustained internal flow allows both structures to extend far beyond the point where formation originally began, during sediment. Brinacle walls are active boundaries where heat transfer, salt exclusion, and fluid motion remain tightly coupled during winter.
The frozen shell is not perfectly pure or impermeable, especially during rapid laboratory growth. Gravity guides freezing below. Local wall defects can redirect brine and generate branching or double-walled morphologies. Chemistry steadily modifies exchange below.
Competing channels may merge when their thermal fields overlap within the same surrounding water. Turbulence limits flow below.
Computer models test how coupled fluid dynamics and freezing reproduce the laboratory structures. Convection steadily redistributes formation below. The same physical framework can be explored under conditions impossible to reproduce directly on Earth. Cooling acts thermally.
Scientists have proposed that brine drainage beneath ocean-world ice could create structures analogous to terrestrial brinicles. Freezing ocean water would reject dissolved salts and concentrate liquid brine within the growing shell. Dilution acts naturally.
If pathways remain connected, dense brine could descend toward Europa's ocean beneath the ice. Flow stabilizes branching below.
No spacecraft has yet observed a brinacle beneath Europa's inaccessible ice-ocean boundary. Density steadily drives structure below.
Different gravity, pressure, and composition could produce structures unlike anything seen beneath Antarctic sea ice. Discharge acts locally.
Models suggest thicker shells may permit larger, more persistent drainage features at the ice-ocean interface during sediment.
Such drainage could move chemically important materials between an icy shell and its hidden ocean. Pressure acts dynamically. Transported compounds might create chemical gradients, although biological consequences remain entirely speculative. Enceladus presents another possible setting where freezing salty water could concentrate and drain brine. Crystallization builds transport below.
Hypothetical brinicles should not be confused with the vapor and ice jets already observed escaping Enceladus during ocean.
Shared physical principles may operate across worlds while producing very different structures and chemical behavior. Mixing acts repeatedly. Earth remains the test case for understanding how cold brine self-organizes beneath floating ice. Freezing acts efficiently.
Improved field sensors could capture the internal conditions of growing brinicles in real time. Salinity shapes exchange below. Simultaneous measurements would connect tube geometry with the invisible brine plume producing it. Transport steadily connects flow below.
Broader surveys could reveal how common brinicles are and which sea ice conditions favor their growth during ice.
Combining environmental maps may eventually allow researchers to predict where brinicles should form. Gravity steadily guides geometry below. Climate-driven changes to sea ice growth could alter brine rejection, though local brinicle responses remain uncertain. Brinicles illustrate local physics, but also belong to the broader desalination process occurring throughout growing sea ice.
Each stage is understandable alone, yet together they build one of the ocean's strangest self-organized structures.
A brinicle grows downward because dense liquid falls first, while freezing seawater constructs a hollow chimney around it. At first glance, this crater lake looks peaceful, yet its deepest water can store a suffocating atmospheric disaster. Beneath glassy water, enormous amounts of carbon dioxide may accumulate silently without bubbles, smoke, heat, or visible warning. One subtle disturbance can lift gas-rich water upward, beginning a chain reaction hidden beneath the calm surface. Instead of flames, an invisible carbon dioxide cloud can spill from the lake and descend across surrounding valleys. Because carbon dioxide is denser than air, it follows low ground rather than dispersing upward immediately after release. When oxygen disappears, flames fade and breathing fails, although the released gas itself remains colorless, odorless, and non-flammable. Animals near valley floors face intense exposure, while creatures higher on slopes may remain above the densest cloud.
A sharp elevation difference can separate deadly air below from breathable conditions only a short distance uphill nearby. After the release, the water may look calm again, concealing the mechanism that transformed depth into atmospheric danger. To understand everything, we must descend through stable layers toward carbon dioxide dissolved under enormous underwater pressure below. Inside rare lakes, a shallow mixed zone can float above deep water, isolated for many years or decades. Dissolved carbon dioxide remains molecularly dispersed at depth, so dangerous concentrations may exist without any visible bubbling whatsoever.
Surface winds circulate upper water, but strong density differences can prevent that energy from reaching the deepest layer.
Most crater lakes never develop this hazard because their water mixes, their gas supply stays limited, or both. Volcanic appearance alone reveals little. Depth, chemistry, stratification, recharge, and time determine whether gas can accumulate dangerously below.
During the Nios disaster, deep carbon dioxide escaped suddenly and overwhelmed communities across low terrain surrounding the crater.
2 years earlier, Lake Monoon released carbon dioxide through a similar rare process, confirming the danger was repeatable.
No lava eruption is required. The violent event comes from dissolved gas leaving water during rapid decompression alone. Carbon dioxide usually harms by displacing breathable oxygen, not by acting like a conventional poisonous or combustible gas. Following one molecule reveals how volcanic carbon travels from deep rock into water, then eventually reaches the atmosphere. Far below ground, Magma releases carbon dioxide that migrates upward through fractures long after visible eruptions have ended. Along hidden pathways, volcanic gas moves through porous rock and hydrothermal systems toward the deepest part of lakes.
Old mineral springs can deliver carbon dioxide directly into bottom water, continuously recharging the concealed gas reservoir below.
Under strong pressure, rising bubbles may shrink and dissolve before reaching the surface, leaving no obvious visible trace. Surrounding water molecules accommodate carbon dioxide in solution, storing gas without creating a separate visible bubble phase there.
Lower temperatures also favor gas solubility, helping cold, deep water retain carbon dioxide more effectively than warm water.
Minerals and dissolved substances increase bottom water density, strengthening the separation between deep and shallow layers over geological time. Across the chemocline, small density changes create a powerful barrier that suppresses vertical exchange throughout the water column.
Wind energy stirs the surface repeatedly, while the lower reservoir remain largely untouched beneath the stable density structure.
Rainfall can refresh upper layers, yet fail to overturn the heavier gas-rich water resting far below safely. When particles meet the density boundary, they spread sideways, visually demonstrating why vertical mixing becomes strongly restricted there.
Over many seasons, volcanic recharge adds carbon dioxide faster than natural mixing removes it from the deep basin. Depth profiles reveal the hidden inventory growing near the bottom, while the lake's surface continues appearing completely ordinary. Continued gas input matters because a stable lake can approach dangerous concentrations gradually, without any single dramatic warning.
Saturation, even modest upward movement can let dissolved carbon dioxide form bubbles and change the water's buoyancy. A sealed carbonated container stays quiet under pressure, offering a simple analogy for gas-rich water at depth. Opening that container lowers pressure, allowing bubbles to appear rapidly, just as lifted lake water begins suddenly degassing. As bubbles expand, the water-gas mixture becomes lighter, rises faster, and experiences still lower surrounding. This feedback can transform a few bubbles into a powerful plume, capable of mobilizing a much larger reservoir.
For years beforehand, the layered lake may remain stable, demonstrating that stored energy does not guarantee immediate release.
A landslide could lift deep water, but evidence does not prove that this mechanism triggered every historical event.
Cold rain or seasonal cooling might disturb stratification by pushing surface water downward and displacing deeper layers upward. Internal waves can raise the hidden boundary locally, carrying gas-rich water closer to pressures where bubbles form.
Earthquake shaking is another proposed trigger, although strong shaking is unnecessary once decompression feedback has already fully begun. Because direct observations were absent, scientists distinguish uncertain triggers from the well-supported physics of runaway gas release today. Once deep parcel rises, surrounding pressure falls, and its dissolved carbon dioxide approaches the critical bubbling threshold. Microscopic bubble nuclei then grow within the water, marking the transition from stable solution to unstable two-phase flow. The bubbly mixture weighs less than neighboring water, so buoyancy starts lifting it without continued external forcing afterward. During ascent, decompression creates additional bubbles, stretching the original parcel into an accelerating vertical plume through the depths. Every upward meter lowers pressure further, enlarging bubbles and strengthening the buoyancy that drives additional upward movement continuously. Nearby deep water becomes entrained into the plume, greatly increasing the volume participating in the developing eruption rapidly. The rising column can transport cold water, dissolved minerals, and carbon dioxide from near-bottom depths toward daylight above. At the surface, gas expansion creates a towering water fountain despite the complete absence of combustion or magma. Violent waves radiate across the basin, while the central plume continues drawing material upward from the deep reservoir. When iron-rich deep water meets oxygen, reddish discoloration may appear, but that color is not the lethal agent. Above the fountain, carbon dioxide separates from water and begins forming a dense atmospheric layer over the lake. The self-reinforcing plume continues until accessible gas concentrations and pressure conditions can no longer sustain rapid upward flow. Afterward, foam collapses and reflected waves fade, leaving a reorganized lake that may still contain dissolved carbon dioxide. The eruption transfers part of the gas reservoir into the atmosphere, where terrain controls the next dangerous phase.
In reality, the gas is invisible. Any pale layer shown here exists only to explain its movement clearly. Carbon dioxide makes the released mixture denser than the surrounding air, encouraging it to remain near the ground longer. Through the lowest crater opening, the gas can spill outward and behave like an unseen atmospheric flood downhill.
Valleys channel the cloud downhill, while ridges and local terrain reshape its direction, depth, concentration, and duration substantially. As carbon dioxide occupies low air, breathable oxygen is displaced upward beyond the reach of people and animals. Human bodies can lose consciousness quickly when oxygen drops severely, even without pain, smoke, or obvious irritation beforehand. Small flames may extinguish inside concentrated carbon dioxide, providing a visible warning that breathable oxygen has become scarce.
Higher terrain can offer protection because dense gas preferentially fills hollows, valley bottoms, and other low areas first.
Strong wind dilutes the cloud by mixing it with normal air, gradually restoring oxygen across affected terrain below. Shelter depressions may retain dangerous concentrations longer because weak airflow cannot disperse the dense gas efficiently enough there. Unlike fuel vapor, carbon dioxide does not ignite, burn, or detonate after leaving the lake and entering air.
The main hazard produces neither searing heat nor conventional blast burns. It removes oxygen from the breathing environment.
Ordinary fog contains suspended droplets and follow different physics, although both can visually occupy low terrain temporarily nearby. Smoke usually carries particles from combustion, whereas a limnic carbon dioxide cloud can remain completely invisible to observers. Only instruments reliably detect carbon dioxide concentration, because human senses provide little or no warning before dangerous exposure. Sudden dizziness, confusion, weakness, and collapse can occur when the surrounding atmosphere no longer supports normal respiration properly. Rescue teams require supplied breathing air before entering low areas, since unconscious victims may lie inside concentrated gas.
Livestock and small animals can face earlier exposure because their noses remain closer to gas accumulating near ground.
Following an eruption, residual dissolved gas may persist at depth, requiring new measurements before scientists judge future stability.
The restored calm surface can mislead observers, because catastrophic atmospheric consequences leave limited visible evidence on the water. Researchers lower probes through the lake to measure temperature, conductivity, pressure, density, and other changing depth-dependent properties accurately.
Layered measurements reveal whether the water column remains strongly stratified and where important chemical boundaries currently sit underwater. Pressure-preserving samplers capture deep water without premature bubbling, allowing dissolved gas concentrations to be measured accurately afterwards safely.
Controlled laboratory depressurization releases the captured gas safely and helps calculate how much remained dissolved at depth originally. Repeated surveys show whether carbon dioxide inventories rise, fall, or shift as degassing and recharge continue over time.
Scientists combine lake depth, gas profiles, and topography to model how future releases might travel across nearby valleys. Engineers place a vertical pipe from a floating platform down into the deepest gas-rich water layer below.
Inside pipe, rising water experiences lower pressure and begins releasing carbon dioxide as rapidly expanding bubbles form. Those bubbles lighten the pipe contents, creating self-lift that continuously pulls more deep water upward without mechanical pumps. At the outlet, a controlled fountain vents carbon dioxide gradually, reducing the reservoir before runaway conditions can develop. Moving air disperses the released gas, while degassed water falls back across the lake's surface beneath the fountain.
Because most carbon dioxide has escaped, returned water joins upper layers without rebuilding the same concentrated bottom reservoir.
Multiple pipes increase removal capacity, shortening the time required to reduce a large, dangerous dissolved gas inventory safely. Season by season, monitored degassing lowers total dissolved carbon dioxide and increases the margin below critical saturation levels.
However, geological recharge continues, meaning pipes and surveillance may remain necessary long after emergency gas concentrations decline significantly. As deep concentrations fall, fountain performance changes because less gas is available to drive the self-lifting flow upward. Intake depth must follow remaining gas-rich layers while avoiding sediment disturbance and unnecessary destabilization near the bottom. At Lake Nyos, engineers also assess the natural dam, a separate downstream hazard independent from carbon dioxide release. Buoys, weather stations, gas probes, and slope sensors together provide a broader picture of changing lake conditions continuously.
Communities practice moving toward higher ground because elevation can reduce exposure during a future low-level gas release. Lake Monoon also received controlled degassing systems after its disaster demonstrated the same fundamental carbon dioxide release mechanism.
Lake Nyos became an engineered monitoring site where gas removal, measurements, and maintenance transformed the regional risk landscape.
Lake Hivu contains carbon dioxide and methane at much larger scale, but its chemistry and dynamics differ substantially.
Therefore, every gas-rich lake demands site-specific analysis rather than direct assumptions based on another basin's unique history.
Many crater lakes remain harmless because they are shallow, frequently mixed, weakly recharged, or chemically unsuitable for accumulation. Danger requires several ingredients together: sufficient depth, persistent gas input, stable stratification, and enough time for substantial storage. Climate-driven changes in rainfall or temperature may alter mixing, although outcomes depend strongly on individual lake structure locally.
Changes in volcanic recharge can modify deep gas inventories even while the surface provides no visible indication above.
Microbes reshape chemical cycling within layered lakes, but deep magmatic carbon dioxide remains the primary Nyos-type gas source. Autonomous profilers can repeatedly track water column changes between expeditions, improving detection of gradual instability or renewed gas.
Satellite observations reveal surface disturbances and surrounding landslides, but cannot replace direct measurements of deep dissolved gas inventories.
Scaled laboratory experiments reproduce decompression, bubble growth, entrainment, and plume acceleration under carefully controlled physical conditions safely indoors. Numerical models identify thresholds separating stable storage from runaway degassing, helping researchers interpret incomplete field evidence more reliably. Uncertainty remains greatest around initial triggers, not around the established roles of dissolved gas, pressure, and buoyancy afterward.
Early warning works best when deep measurements, weather, slope monitoring, communication, and evacuation planning operate together continuously locally. Community drills translate invisible scientific risk into practical movement towards safer elevation before an emergency actually occurs nearby.
Globally, only a small number of lakes combine the unusual conditions needed for catastrophic dissolved gas accumulation naturally.
From one molecule to an entire valley, pressure and gravity scale microscopic dissolution into a regional natural hazard. Now the calm surface appears differently, because invisible depth structure matters more than the lake's peaceful appearance above. The lake explodes without fire when deep carbon dioxide escapes water, accelerates upward, then floods low terrain silently.
This small lizard escapes predators by diving underwater and repeatedly breathing from a silver bubble attached to its snout.
Water anoles inhabit tropical stream margins where dense vegetation, wet rocks, and moving water provide immediate underwater refuges.
Their streamside habitat places branches, roots, and climbing surfaces directly above pools, channels, and concealed submerged shelter.
Perching close to water lets the animal disappear from danger within seconds, before many terrestrial hunters can react.
Birds, snakes, and other predators create intense pressure for rapid escape behavior along exposed rainforest stream banks. Before diving, the lizard evaluates distance, cover, current, and the nearest safe route beneath the water safely.
A sudden leap carries the animal below the surface before most land-based predators can follow or accurately track it.
Once submerged, depth, darkness, ripples, and visual distortion make the small reptile surprisingly difficult to locate from above.
Strong toes and curved claws help it remain anchored against flowing water while hiding beneath rocks or roots.
The extraordinary respiratory behavior begins when air leaves the nostrils and forms a bubble instead of floating away. Hydrophobic scales help exhaled air remain connected to the face, keeping the bubble accessible beside both nostrils. Semi-aquatic anoles possess scale features associated with stronger water repellency and more reliable underwater bubble retention. The nasal bubble may connect with a broader reflective air layer trapped against hydrophobic scales across the head.
Air moves through the nostrils while the mouth stays closed, preserving a compact respiratory circuit beneath the surface.
The lizard inhales from the bubble, exhales back into it, then repeats the same cycle during submersion. Every breathing cycle changes the bubble's composition because metabolism consumes oxygen while tissues continuously produce carbon dioxide.
Oxygen follows the ordinary vertebrate route from the lungs across thin tissue and into the circulating bloodstream.
Rebreathing extends the usefulness of existing lung air, rather than creating an entirely new respiratory organ underwater. Measured oxygen decline inside the bubble confirms that its trapped air actively supports the submerged animal's respiration. Repeated inhalation lets the lizard reuse air that would otherwise escape immediately toward the stream surface after exhalation. Recycling stretches the useful duration of a limited air store, while the animal remains concealed during a defensive dive. Each extra underwater minute increases the chance that a searching predator leaves before the lizard must resurface. Staying below the surface allows currents, shadows, and ripples to erase the original location of the sudden escape. Recorded submersions vary greatly because body size, stress, temperature, habitat structure, and individual decisions all influence duration. Some semi-aquatic animals have remained underwater for roughly 8 minutes, although most defensive dives are considerably shorter. A maximum observation reveals biological capacity, not the routine dive length of every animal under natural conditions.
Body size, water temperature, current speed, and disturbance can all change how long a submerged lizard remains hidden.
Smaller and larger animals carry different lung volumes, metabolic demands, and bubble surface areas relative to body mass. Remaining nearly motionless lowers oxygen consumption, allowing the bubble's limited respiratory value to last substantially longer under threat. Sheltered positions behind roots and stones reduce physical effort while hiding the lizard from movement above the water. Calm pockets behind obstacles demand less energy than exposed current, where the animal must constantly resist downstream force.
Moderate flow can refresh gases around the bubble without tearing the delicate air layer away from the snout. Carbon dioxide readily dissolves into water, creating a possible route for respiratory waste to leave the bubble. Because carbon dioxide is highly soluble, surrounding water may absorb it faster than oxygen disappears from the reservoir. An exposed bubble water boundary could therefore remain useful longer than a completely sealed pocket containing the same air.
Metabolic carbon dioxide travels from active tissues through blood toward the lungs, even while the lizard remains submerged. Exhaled carbon dioxide enters the nasal bubble, where some molecules may diffuse outward into the passing stream. Carbon dioxide removal is physiologically plausible, but recycled stored air remains the mechanism supported most directly by experiments.
Underwater rebreathing combines ordinary lungs, hydrophobic skin, trapped air, and a dynamic gas boundary beside the nostrils. The respiratory loop begins with oxygen already stored inside air, carried beneath the surface during the initial dive.
Bubble oxygen concentration falls predictably while a living lizard continues breathing repeatedly from the attached reservoir underwater.
Researchers compared that decline with artificial bubbles held underwater under similar physical conditions, but without breathing animals.
Control bubbles retained oxygen more consistently, demonstrating that biological respiration caused the stronger decline seen with lizards. Those measurements confirmed that the nasal bubble functions as an extension of the animal's existing pulmonary air supply. Oxygen enters the lungs during inhalation, while mostly unused nitrogen returns to the bubble during the following exhalation. As oxygen decreases, nitrogen occupies a greater fraction of the remaining bubble, and the respiratory mixture becomes progressively poorer.
Eventually, available oxygen falls below a useful level and contributes to the lizard's decision to return toward air. The animal releases its underwater grip, swims upward, and breaks the surface to obtain a completely fresh breath.
At the surface, the depleted bubble merges with open air, while the lungs refill within a single respiratory cycle. After climbing onto a nearby rock, the lizard restores normal oxygen delivery while monitoring the streamside environment for danger. Heart rate, breathing, and movement gradually return toward ordinary levels as the animal recovers between defensive dives.
Another predator may appear before recovery finishes, forcing the lizard to repeat its underwater escape under greater physiological pressure. A second dive creates another nasal bubble immediately, showing that the behavior is repeatable whenever danger returns.
Every resurfacing restores a fresh gas mixture, replacing the oxygen-poor reservoir produced during the previous submerged interval. Across a single day, repeated cycles of diving, rebreathing, resurfacing, and recovery may occur around the same stream refuge.
Underwater movement may also support exploration or foraging, although predator avoidance remains the best established ecological function. Submerged stones, roots, and leaf pockets contain potential prey, as well as concealed resting places away from terrestrial hunters. The lizard balances underwater opportunity against limited oxygen, physical effort, and the continuing need to return for atmospheric air.
Scientists tested the bubble's actual respiratory value by experimentally preventing its normal formation during controlled defensive dives.
Hatched lizards entered identical water chambers, differing mainly in whether the familiar nasal air bubble remained available. Control animals preserved their ordinary hydrophobic air interface and continued cycling exhaled gas beside the nostrils underwater. A temporary surface treatment disrupted bubble attachment without changing the chamber's water temperature, depth, or overall handling conditions. After treatment, exhaled bubbles detached from the face and floated upward before the lizard could inhale them again. Those animals relied mainly on their initial lung supply because reusable gas no longer remained beside the nostrils. Lizards retaining normal bubbles stayed submerged substantially longer than animals whose external air interface had been disrupted. In that experiment, ordinary rebreathing increased average dive duration by approximately 32% under otherwise matched conditions.
Comparable body sizes, chambers, and handling procedures strengthen the conclusion that access to the bubble caused the difference.
The result demonstrated that the air pocket performs a functional respiratory role, rather than merely reflecting trapped surface air. However, the experiment did not show permanent underwater breathing, unlimited oxygen renewal, or complete independence from atmospheric air. The bubble remains a finite reservoir, whose volume and gas composition continue changing throughout every submerged breathing cycle. Recycling improves how the initial air supply is used, but it cannot prevent eventual oxygen depletion during long dives. Possible carbon dioxide loss across the bubble surface may further delay the point when resurfacing becomes physiologically necessary. Gas may move in both directions across the interface, although each proposed exchange process requires separate experimental evidence. Confirmed rebreathing, plausible carbon dioxide removal, and emerging oxygen uptake evidence therefore occupy different levels of scientific certainty. Successive studies progressed from behavioral observation toward gas measurement, bubble disruption, and controlled environmental experiments over several years. Natural dives remain essential because laboratory mechanisms evolved to solve ecological problems along predator-filled tropical streams.
In the wild, bubble-bearing lizards hide beneath ledges and roots, while threats continue searching along the bank above.
An extended dive allows danger to move farther away before the concealed animal cautiously returns to the surface. Comparative research revealed that underwater bubble rebreathing appeared independently in several distantly related semi-aquatic anole lineages. Separate evolutionary branches developed remarkably similar diving behavior, despite lacking one recent bubble-breathing common ancestor within Anolis. Streamside species from different American regions encountered comparable combinations of predators, water access, and underwater shelter near flowing water. Those recurring ecological pressures repeatedly favored escape strategies that turned nearby streams into temporary defensive refuges during attacks. Across independent lineages, threatened lizards entered water and formed accessible nasal bubbles using similar behavioral sequences under threat. Ordinary anal skin already possessed water-repellent microstructure before specialized underwater rebreathing evolved within semi-aquatic species. Natural selection likely co-opted that existing surface property, giving hydrophobic scales an additional respiratory function underwater. Water repellency may originally support self-cleaning or surface protection, while later becoming useful for stable bubble retention. Semi-aquatic forms maintain more persistent external air films that remain attached during movement beneath the water surface. The accessible air concentrates near the nostrils, allowing repeated inhalation while the lizard keeps its mouth closed underwater. Different species vary in bubble size, attachment area, head shape, and the number of threads within their air layer.
Convergent solutions still reflect each species' body dimensions, scale texture, habitat, and preferred underwater hiding behavior underwater.
Local stream conditions can determine which bubble geometry and diving strategy produce the greatest survival advantage locally. Fast rocky channels and slow shaded pools impose different costs through current strength, oxygen availability, and concealment. Calm water reduces the energy needed to hold position, though surrounding gases may refresh differently than in strong flow.
Water containing more dissolved oxygen creates stronger conditions for oxygen to move toward an attached underwater bubble.
Researchers therefore compared dive duration across chambers containing low, intermediate, and high dissolved oxygen concentrations in controlled trials.
Lizards remained submerged longest in the highest oxygen treatment, when water movement was kept relatively low and controlled.
Separate experiments manipulated dissolved oxygen and flow independently, preventing one environmental variable from masking the other's effect.
With oxygen held constant, slower flow treatments also produced longer dives than faster-moving water inside the experimental chambers.
The combination of adequate dissolved oxygen, low physical effort, and a stable bubble suggested an additional respiratory possibility.
A true physical gill would draw some dissolved oxygen from surrounding water into the bubble during submersion.
Aquatic spiders and insects already use air films or bubbles that exchange respiratory gases directly with water.
Across such interfaces, oxygen can enter from water, while carbon dioxide leaves through the same exposed boundary.
The animal bubble changes volume and shape during dives, potentially recording several simultaneous gas movements across time.
Closed reservoir and physical gill models predict different oxygen trajectories, bubble volumes, and achievable underwater durations for the animal. Longer dives in oxygen-rich water match one important prediction expected from partial physical gill activity underwater. However, researchers have not yet measured continuous oxygen flux directly across the bubble's surface during natural rebreathing.
Future microsensors could monitor gas movement at the interface without disturbing the lizard's behavior or hydrophobic air layer.
Simultaneous oxygen, carbon dioxide, and volume measurements would reveal how storage, waste removal, and replenishment interact underwater.
Portable field sensors can connect controlled respiratory mechanisms with temperature, flow, and dissolved oxygen in occupied streams.
Wild lizards frequently perch near stream sections offering manageable current, adequate oxygen, and nearby underwater cover during danger.
Roots, ledges, and cavities provide better concealment than open banks, even when respiratory conditions are otherwise similar.
Seasonal rainfall, sediment, temperature, and vegetation can alter both the quality of refuges and bubble performance throughout the year.
Warmer streams hold less dissolved oxygen while simultaneously increasing the lizard's metabolic demand during underwater hiding at the same time. Shaded